Okay, so we're going to be talking about Chapter 4, Topic 4, Network Communications and Security, um, talking about network protocols. Some of the things we're going to be talking about are, some of the different protocols that are used, in the stack, in the networking stack, application transport network layers. We'll talk a bit about MAC, what we call medium access control, and data link layer technologies. All right. So book-wise, chapters 3 through 6, 3 application layer protocols, B transport layer protocols. Chapter 5, pieces of chapter 5 will be network layer protocols, and then 6 will be MAC and data link layers. All right. So protocol. So we'll start off talking about what is a protocol. Um, if you think about TCP/IP as a communication tool or mechanism, there's a lot of different pieces. So it's not just TCP/IP. There's a lot of components and different types of pieces and different kinds of functions that are built into it, baked into it, that make up the whole of TCP/IP. As a matter of fact, TCP IP are really two separate things. One is TCP for Transmission Control Program, and IP, which is the Internet Protocol. All right. So there's a whole bunch of different types of examples of protocols. So as we go through the list here real quick, SMTP is used for email, basically simple mail transport protocol. HTTP obviously was introduced with the web. Hypertext transfer protocol specifically for web pages. FTP, a very mature file transfer used for upload and download files. UDP stands for User Datagram Protocol, and it's used for connectionless, used in concert with IP for connectionless types of communications. Internet IP is Internet Protocol. It's really the main delivery mechanism for information on the internet. TCP/IP, a whole series of functional capabilities enable you to kind of dismantle, you kind of break down and reassemble data and send it across the network. ICMP, Internet Control Message Protocol, is a utility language or utility protocol that's used to by routers to exchange information back and forth. SNMP, which is different than SMTP. SNMP is a simple network management protocol. It can be used to collect information from computers, like for example, performance information, memory, CPU, things of that nature. And then Telnet. Telnet is a utility program. Basically, enables you to execute commands on a remote computer, connect to a remote computer, um, communicate with it, be able to execute commands on that. So this list of protocols is really a kind of an example. There's other ones out here. There's other ones built into TCP/IP. So when we're talking about TCP/IP, uh, in particular, it's not a one thing. It's a whole. Think of it as a bag of stuff, all sorts of different pieces, different functionalities, all kind of working together. So an application, when we're talking about an application layer protocol, basically it's an agreement on, really what it is an agreement on a set of rules. All right, say syntactical and semantic rules. Basically, how to, this is what comes in, this is what goes out. Here's the structure. This is what the content is. So we define the format, the exchange messages, and the orders. And when you put those two together, format and order, you have what you need to be able to exchange information. All right. So when we talk about syntax, we define the format of the exchange messages. And once again, with computers, networking computers, precision counts. If something is unclear, then then it cannot be processed usually. Um, there's an information flow. When we talk about this application layer, we're focused on things like information flow and the precedence relationships. Because a lot of times what will happen is with communications. Stuff can be broken up into different pieces and kind of sent down the wires and reassembled. So part of the challenge, especially at the application layer, is to reassemble this stuff and put it together in the right sequence as you be, so you'll be able to process the data. So there's a couple different types of what we call interaction models, and there's really two big ones. One is client server. So basically, there's a server is a large centralized computer. It can be set up as a shared resource that clients, what we call hosts, can either a client, which is a standalone, which is like a PC. So if you think about a PC and a web server, that's a client server model. A phone and a web server is a client server model. So it's been around about maybe 30 years now, something in those lines. But it makes up, it is the way the internet operates. The internet is a client server model. Peer-to-peer networking is, everything has the capability of both being a server and a client built into it. So so this idea of being able to communicate directly with other machines, and be able to create like a mesh environment where every machine is connected, has the ability to connect to every other machines. Right. So you see a whole bunch of different areas, internet telephony, things like Skype, file sharing, internet access wide, file systems, and things of that nature. So it's kind of you'll see not quite as common as client server, but you see a fair amount of it out there. So DNS. So DNS stands for Domain Name Service. And basically what DNS does is it makes the internet addressing usable by humans. Okay, so what happens is it will replace the internet address, which is a 4-octet number, dot 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 dot, or xxx dot xxx dot xxx dot xxx, which is the unique internet address. And what it will do is actually allow it to use things like www.google.com or www.amazon.com or NewYorkTimes.com or ABC.com or anything you would anything you would have out there. And all it is really a table. It's an address translation, which if you look at, there's a table inside of DNS which has what the name, the human readable name, and what the matching address is. And what it lets you do is let you map the names to the corresponding IP addresses, and you can deal with the IP addresses as kind of on and behind the scenes as technical things, and not necessarily have people wallowing in those types of details. Because quite frankly, if everybody had to use IP addresses only, I suspect that the penetration of utilization of the internet would be nowhere near what it is today. So kind of an example here, what we call domain names. So this is actually something that's registered, by, there's an internet organization that manages this and assigns these different names. So you'll see, some of our more familiar ones like, .edu for schools, .gov for government. Some countries, so you got France, you just say DEs for Deutschland, which is Germany. And you see kind of this hierarchy. The ones we see almost more than anything else is, called .coms, all right, which stands for commercial. All right. It's a first come first name basis, and you can register the name if you're the first person to do it. And as we say here, .gov is reserved for U.S. government. It is international organizations. EDU is for educations, and then this kind of country specific is reserved for companies, inside of a particular country. So this is just a quick example, kind of a walkthrough of what the DNS server does. What happens is from our perspective, we enter data into the a browser, all right, and a name, a human readable name, and then what it will do is the browser will communicate with the DNS server. It will check for local. Um, It'll check for what the matching address will be, and pass that address back to the client, to the browser, and initiates the connection using the IP address as opposed to the name. So this is all happens behind the scenes. This is kind of communication back and forth. And in addition, DNS servers are also in communication with other DNS servers. So the namespace is actually distributed across the internet, so we can find things at multiple hops away, multiple far distant locations. We're able to enter a name and be able to get the information. So email. So email's been around a long time. So there was one of the earliest innovations we saw with the internet. He says it consists of four components: basically a message format, basically what does an email look like, what's the mechanisms for transferring between a host and a server, exchanging of messages, client software, which lets you interact with the email system, and then the exchanging, kind of an email exchange. So it's pretty much it's a pretty straightforward. Everything we see now when you see Gmail and stuff, behind the scenes it looks very much, if you kind of strip everything down, but they all kind of work the same way, right? And email messages really are two parts. One, we've got a header, which describes the message, and two is the body, which actually is the message or contains the content of the message that you're sending. MIME is a communication protocol, multi-purpose internet mail extensions, which is a type of mail protocol. Some new types of header lines and types of ways of being able to communicate, be able to transfer data over email. So delivery mechanisms, email delivery mechanisms. So the earliest one is SMTP, still around. A couple other ones you may have heard. So there's between DNS servers. We talked about DNS servers talking to each other. Actually, they use their own mail protocol, MX, Mail Exchange Protocol, was actually in DNS. POP, you might have heard POP, Post Office Protocol, also a fairly well used, kind of old protocol. Most modern stuff now uses IMAP, Internet Message Access Protocol. So, basically these things are all kind of operate in their own network, so they can run side by side with each other. If you want some more information, you can actually take a look at this link here, which will take you to a YouTube, which shows you, a little brief video about what's the difference between POP and IMAP. So SMTP, communication. Everything you see here with this RFC. RFC is a definition of a function or some sort of component inside of TCP. RFC stands for request for comment, which is the mechanism by which new features and new functionality is added to TCP/IP. So this is just some of the information of kind of what is in SMTP. It's a client server protocol for email messages. Listening on port 25. POP, very simple. Listens on port 110, 3 parts, authorization, a transaction where you download the messages, and then an update. So it's POP is very simple. You saw a lot of POP, especially earlier implementations on the internet. And then IMAP. IMAP is really a more powerful, kind of the next generation. It allows you to do things like two-way synchronization, multiple client devices. Provides functions to search, download, delete, filter messages. A lot of stuff you see now, like Microsoft Exchange. Um, you know, the kind of industrial size and industrial scale email systems, or will usually use IMAP. FTP, file transfer protocol. FTP is a mechanism by which you can copy files from one system to another. All right, you can browse a file system. There's a whole series of commands that do it. Very heavily used. Originally, early on, accessing the internet was actually one of the early things you could use that people were using on the internet, moving data from one system to another. You can use authentication or what we call anonymous. So you can enter simply a user ID and email address as the password, then be able to create a kind of a specialized zone. This is obviously not secure. This is obviously authenticated. It is secured. Anonymous is not secured. All right. So there's certain scenarios where you'd want to use anonymous, but it's not necessarily across the board. Hypertext. So hypertext is the format that supports the World Wide Web, which is part of the internet. So part of that is the addressing scheme that is structured to be able to allow for like URIs. All right, is it called Uniform Resource Identifier, URI, URLs. It basically uniquely identifies a resource on the web. Standard document format for HTML or XML, and standardized protocol for retrieving documents off the server. As we said about the internet, but the web, it's actually fairly simple. All right, obviously, there's moving parts, and there's a lot of terminology you have to kind of grasp, but the mechanics of it are fairly simple, which is actually one of the reasons it's become as powerful and as large as it is. A URI, which is user resource identifier, basically the addressability of something on the internet that you can find it and retrieve. HTTP, this is the transport protocol. So HTML is the format structure. HTTP is the transport protocol that's used on the internet. Some of the information, it runs on port 80 and sends a request. Once again, it's a client server configuration. So a client sends requests to servers, and the servers will return the response. Just the structure of what an HTTP message looks like. And this is like a request. Think of it as a request response. Okay, you send a request in, from the client will send the request in, server will respond back. All right. This is a brief video, if you want to take a look on YouTube, from kind of an introduction to HTTP. So this is some details around reliable transport protocol. One of the things, the question of reliable versus unreliable is really, it's mostly reliable. We say unreliable is just simply not verified. All right, it doesn't mean that it's bad or negative. It simply means that the overhead associated, it does not do just a verified checking of all communications back and forth between a client and the server, and therefore you reduce overhead, which therefore makes it run faster. But it would be potentially subject to errors if something was to come along. So this article right here, actually this video right here, will give you an explanation of the difference between TCP/IP and UDP. Okay, so UDP, user datagram, This is used for connectionless, they say unreliable connectionless transport. Um, Very fast. So actually, a lot of stuff runs over UDP. You actually will go out and you'll see on your PC or your phone. You'll see a lot of different types. You'll see a lot of use of both UDP and TCP/IP. It's not one. It's not one replaces the other. It's there's a need for each one, which gets as you determine what your um, requirements are, will determine what you want. Whether you want to run one or the other. Just some of the information about UDP service. Kind of no guarantee of delivery. Does not deliver. You know, so things like desequencing and losses are not necessarily reported. So usage, where you want to use UDP, where you want to where you want to be fast, and where losses are not as impactful, can be recovered. So short requests, so like things like UDP, like DNS, RPC, DNS, remote procedure calls, NFS, network file systems are all UDP. Or voice over IP, video over IP. Streaming is usually done over through UDP. TCP is basically a connection oriented. So it's a reliable byte, they call it a reliable byte stream, connection oriented transport service. So 90% of the data exchanged in the internet is TCP. Used by a whole bunch of things. World Wide Web, email, most transport protocols, remote access, flash, most internet. So it is significant. It makes up a significant portion of the traffic that runs on the internet. So connection establishment basically, in order to be able to be connection oriented, you have to establish a connection. So there's actually what we call a three-way handshake between the two parties, kind of initiating a connection, verification, acknowledgement, and synchronization. So once that's established, then the communication will flow between the two, between the client and the server. So network protocols, the YouTube video here for the network protocol. You can send a segment to any destination without understanding anything about the underlying network, which is the secret sauce of the internet. If you think of internet as a mail system, we don't necessarily need to track a letter as it flows through a mail system. We basically put the mail letter in the mailbox, in with the expectation it will find its destination. The way the internet is designed, you put a packet on the internet and it will find its way to its destination. All right. So the network layer is really the glue that kind of holds all this stuff together and hides all the. It does a good job of hiding all the underlying complexity, and it allows for the transport of information across the internet. A couple, just some design principles here. Each network layer addressed independent of data link. So layer 2, layer 3. Network layer is also what we call layer 3, which is the router layer as well. It does not have any dependencies on the lower level. Most, the network layer, as we say here, is actually the kind of, as you look at it, the implementations, there's really two things. One is the data plane, which is how you move data across the internet. Be able to transfer from one system to the other using routers and exchange of packets. And then there's a what we call a control plane, which is a means by which all of the routers and all the devices communicate with each other to exchange address information and be able to provide pathing so a packet can find its way across the internet without necessarily knowing when it was put onto the network, where it, exactly where the location was going to end up at. So network service types, you can use um, unreliable connection to service, internet protocol, or connection oriented. So you see a lot of, for network service, a lot of IP. IP is really kind of the major, but you can also run things like ATM and frame relay and other types of connection oriented services. Some of the mechanisms, we just kind of talked about that, the ability to, there's really two features. One is you move data from place to place. Number two is you identify the paths, set the roads up. If you can imagine, it would be like setting the roads, putting the off ramps, putting the signs on the network, and then the data plane is actually just moving the data across that. Static routing. So static routing is by default, what will happen is routers will learn and understand and exchange information amongst themselves, and it will determine, the path a particular packet should follow. However, you can, in this, what we call this control plane, we can actually override all that and just put a static route in. See a fair amount of static routes. I see a lot of static route configurations in systems and networks. Basically, you want it to follow a particular path from A to B to C to D. The downside would be if if something gets lost along the way. By default, on the internet itself, it can find an alternate path. If you hardwire it using a static route, if something on that path goes out, then it stops or it does not connect. IP, internet protocol, defined RFC 791 was defined for IPv4, which is the kind of the older, well-established, kind of what we think of as the internet, which is distinct from IPv6, which is the new, basically the new protocol, which has all sorts of nice features, but unfortunately is not necessarily bit compatible with IPv4. So there's a migration that has to take place in order to get from V4 to V6, and that has taken very long periods of time to be able to move ourselves forward with that. This is just some examples, some diagrams of what a network, from a sender, as things go down the stack, across, then back up the stack. Do a send and a receive. So we talked briefly IPv4. This is what we think of as kind of the TCP/IP everybody uses. The addresses on it are fixed size to 32 bits. This is actually has been a huge issue with the internet, because what happens is with 32 bits, the size of the address, how many addresses you can carve out is determined by how many bits you have. With 32 bits, there was a limitation of about 4 billion or so addresses on the internet. However, which was seen at one point in time to be a large number. As we've discovered, we've gone above 4 billion. So one of the key drivers around IPv6 is what we call something called IPv4 address exhaustion. We run out of addresses. All right. So 32-bit is the kind of is our kind of the current state right now. And what's happened is that there's all sorts of different tricks and techniques that we've used to be able to extend that, but it's eventually migration is going to have to take place to IPv6 at some point. So the dotted net, as we said, dotted notation. This is the address, an example of an address: A 1 2 3 4 octet, right, which actually translates to a binary, which is a unique address on the internet. So some key terms here: subnets, which are really a kind of a grouping, an organization of hosts based upon the network. Basically, you have a you have a overall network, and then you have kind of structure it out, across different, based on different criteria. Um, Subnets, is built baked into TCP/IP. You basically apply what we call a mask to which identify the number. What is the addressing scheme? Basically, what is how do we identify what portion of the overall address is the subnet? All right. So V6, defined in RFC 1752. Um, Addresses are 128-bit fields. All right. Actually, some pretty significant improvements. The header is a format. It's designed specifically to be parsed by hardware devices. You can configure IP v6 addresses automatically. It is security integrated. IPv4, basically, security was an afterthought, which was one of the challenges we've seen with the internet. A lot of the vulnerabilities we're seeing, is the fact that there was nothing built, there was nothing there originally, and then a lot of the stuff that came on board was kind of a bolt on. So it was not an integrated, design from the ground up, intrinsically secure mechanism. Here's the kind of the structure of an IPv6 address. What you'll see is these use of colons between each of the octets here, as opposed to the dots, which is the IPv4. Just some more details around what these packet formats look like. Kind of, it's a 40 bytes contain 8 different fields. The structure of a IPv4 and IPv6 is very different. All right, so it's not necessarily, it's not going to be automatically compatible. All right. Now, some stuff they've done is they've actually made some significant improvements. One of the things they've happened, IPv4 would allow things like fragmentation in headers, and the problem is that would result in like performance hits. So what happens is IPv6 doesn't allow it, which actually makes improves performance and throughput. Also, it's really designed with the idea of being able to process things quickly. All right, so the idea is it takes it's identified a lot of the some of the bottlenecks that we see in IPv4 that shows up as you start scaling this stuff up, and you get a more consistent throughput as you continue to push larger and larger volumes of data. So there's some real advantages to it. This is the data link layer. This will give you kind of a video here. Will give you a description of the data link layer. Basically, it's the layer that sits between the network and the physical. So the wires, it's the area that actually handles the translation of the signals coming off of the network, the network interface, right off the wire, and then translating that into kind of structuring it and putting it in what we call frames. All right, so this area is, this is the land of switches. All right, so the data link layer deals with frames. It deals with the devices we're looking at, are switches. Below that is the physical, which is actually bits, zeros and ones. Above the data link is the internet layer, the network layer, where we route packets across the internet. All right. So local area networks, you'll see identified unique data link addresses. So this is really closer to signaling and the actual transfer across the wire. So as I said, what it does is it'll pick It'll pick the bits off of, it'll receive the bits from the network and then format them into packets, excuse me, into frames, which will then be, as it moves into the network layer, be converted into packets, which can be routed. So really, you know, this data link layer is really the area where what we call local area networks. All right, so as opposed to a wide area network, which is more kind of the internet and the transfer of information across, um, you know, long distances across wide area networks. LAN organization, a couple different ways you can do this stuff. The most common is what we call a bus network. You go to a physical, everything is connected to one cable and everything just kind of sits on that cable. Um, what will happen, it's interesting because like switches, you'll see you plug all these different systems into a switch, but basically a switch logically, the way it operates is it looks like a bus. So you plug all the stuff into a switch, and it just acts like it's a cable. All right. Some other ways though we've seen rings. Token ring was a ring shaped network. Star networks where everything talks to everything else. Wireless, and we'll be talking more about this further downstream around basically where we're replacing wired connections with radio signals. So MAC is the medium access control. This is where we're transferring the data from the network device, the data link layer, onto the wire, kind of onto the onto communications. What happens is, if you can imagine, if you take, for example, or an example of a bus network where you've got 5 or 6 devices connected onto it, and what'll happen is they'll share information. Each one has got everybody's got an equal access onto the network, and what'll happen is it will connect to the network. Everything's connected onto the network. And when it would send a packet, it would first check to see if anybody else is transmitting, and then it would put a packet on the wire. Now, if 2 machines try to do it at the same time, it's what we call a collision. And what it'll do is it'll identify a collision and then back off for a couple cycles and then come back again. All right, so this is all around. This is all done through the software, the algorithms, and it's collisions are actually something. It's one of the things when we're looking at local area networks, we're measuring, monitoring for things like collisions. A lot of collisions means you've got a lot of traffic, and probably need to maybe do some re-engineering or some kind of take a look at how you've got stuff set up. CSMA, this is a carrier sense multiple access. Basically, this is the mechanism by which all of these machines that are on the same bus handle sending drop using communication across the shared wire. The idea is a carrier sense is before it transmits, it will verify that communications are okay. It can transfer, it can do, and then it will execute that. The multiple access is obviously multiple hosts on the same. So this is actually, there's an algorithm baked into the software that handles all this behind the scenes. So this is just a kind of an example of a wired broadcast network. Collision detection, is if two hosts are trying to send a packet simultaneously onto the network, basically it will detect it and then back off the signal. So this is kind of the mechanics of it. It just describes really the pack, the mechanism by which this stuff is actually performed. Retransmit timeout. Basically, there's what it'll do is it'll set a time. It'll calculate a time of which it will wait and then try it again. So once again, this is the kind of a pictorial version of both stations listening. This one actually puts something on the wire. This will try to transmit while it's in effect, jump on there, basically interfere with the communication that from this first workstation. And then what will happen is it'll detect a collision, back off, and then determine a time when it will retransmit again. So this is CSMA with collision avoidance, actually just kind of an enhancement of that to operate with wireless. All right, so this is just once again some of the details around kind of the mechanisms of structures of what it uses to handle this stuff. Right, Ethernet address, MAC addresses, AKA Ethernet addresses, data link layer addresses, Ethernet addresses, and MAC addresses are kind of an interchangeable. Basically, it's the hardware address of that particular device. The first 24 bits identify the manufacturer. So every manufacturer is assigned a 24-bit prefix, which will make up the first half of the address, and then the second one is actually the identifier. So you'll see, like for example, HP or Cisco or Palo Alto or whoever else. Every one of these will have a different OUI. So when you look at a MAC address, you can figure out, well, what type of equipment just from looking at the address. Right. Ethernet frame. We talked around kind of this idea of frames, getting data from signals, coming on the wire into a structure which it can then be turned into packets. Right. So that's a whole kind of a transformation. That's kind of the initial structure of taking signals and turning them into something as to be processed up the stack. Switches. We talked around switches as they're actually very intelligent. There's a lot of software, sophisticated software that handles these things, and really we've seen huge increases in performance. We're seeing switches are now at 10 gig a second, which is an astonishing amount of data that can be pumped through these things. But once again, the execution operation of these things, relatively simple. So you can, as long as you've got simplicity and you don't have a lot of dependencies, kind of things that are complicated will have more dependencies. More dependencies means you won't, you'll have issues as you try to, push more traffic through. Right. So this is the idea of what a switch will do is it's going to take data off the wire and turn it into and pass frames, structure open frames, and then send frames along. Okay, and that is it for topic 4.